Hello everyone, I hope everyone is doing well. This week we're going to be talking about a few different things, and we're going to start by talking about ocean habitats and their biota. And just a real brief note here about what some of these words mean. So a habitat, we've talked about habitats, but we haven't actually defined the word habitat at this point. A habitat is basically a home for a living thing. For example, if you're a sea otter, your habitat is a kelp forest. Or if you're a reef fish, your habitat is a coral reef. So we're going to be talking about different types of habitats and some of the living things that live in them today. Now, before we get started with today's lecture, I want to talk a little bit about the upcoming schedule because we're coming into the end of the semester, and I want to make sure everyone knows what's going on. So we have 2 weeks left in the semester at this point because we've extended our semester by a week, even though we lost 2 weeks at spring break. This week we will have regular lectures, so we'll have 3 lectures this week. Next week, however, that's going to be the last week of classes, and so we're going to do things a little bit differently. We're going to have one regular lecture, and then we're going to have one review lecture, where I'll go through all the topics of things that might be on your final exam. And then finally, we're going to have one Zoom meeting. And at that Zoom meeting, you can ask me any questions that you would like. Now, of course, you don't have to come to that Zoom meeting. We'll record it. It will be available to you. It will be scheduled during our regular class period on next Friday, not the one this week, but next week. So it'll be from 11 to 12 on next Friday. And that is May the 8th. Our final exam is Wednesday, May 13th at 10:15, okay? And you need to take the exam during that time. If you cannot take it during that time, you need to communicate with me beforehand. All right, I understand that people have all sorts of things going on, and it can be difficult to have internet access and things like that. So we can be flexible with that, but you need to talk to me beforehand, or I will not know that that's what you want to do. All right. So that's something coming up that you guys need to be communicating with me about. If you have not taken quizzes, answered questions, things like that, then you need to start doing that right now, because you basically have 2.5 weeks until your final. I know a lot of things are going on. I'm going to do my absolute best to have everybody do well in the class, but you need to put forth some sort of effort or communicate with me in some sort of way. If you have not, now is the time to do that, okay? All right, let's get started with today's lecture. So we're going to be talking about all sorts of different habitats in the ocean. And we're going to start by talking about the habitats closest to land. And we're going to move out from land to the open ocean. All right, so the first zone we're going to be talking about is the neritic zone. So these are the waters over the continental shelf. All right, so from the shoreline, which would be the littoral zone, or we sometimes call that the intertidal zone. So from the shoreline out until we get to that shelf, that continental slope, okay? So when we think about the neritic zone, we're thinking about the area that's relatively shallow, right? Because it's over the continental shelf. And so this area really has all the ingredients for high biological productivity. The sun can reach most of that area because it's pretty shallow. There are nutrients that are washed into this area from the continents, from down rivers. And then we also have a lot of turbulence here. We have currents, we have waves, we have tides. So put all those things together and we end up with very, very high biological productivity. And that means we have a lot of phytoplankton. We've talked extensively about the idea that diatoms and dinoflagellates are the base of the food chain, and these guys really, really dominate the neritic zone close to land. We've also talked about these guys. So these are copepods. The zooplankton are dominated by arthropods. Arthropods are a group of animals that include things like lobsters and crabs. Barnacles are arthropods, and these guys are arthropods. There are other planktonic arthropods that are in the zooplankton. For example, barnacle larvae, or krill, the euphausiids that are krill. But these guys are really, really important ones when we talk about the neritic zone. And so this really is the basis of the food pyramid here. These guys on the bottom, and then these are the next step up. And they support huge amounts of biomass above them. But I do want to talk about some of the other zooplankton that are out there, because these aren't the only ones. So one of the basic types of zooplankton out there are the jellies. And these are animals that are invertebrates. They don't have any hard parts. They're actually, if you think about them in terms of evolutionary biology, these were some of the very, very early groups of animals. And these jellies here were the first animals to have muscles that helped them move and that had a neural network. So these are pretty important in terms of the evolution of animals on Earth. So let's take a look at how these guys move. You can see that pulsing. Those are muscles. They have a very, very basic neural network that basically pulses those muscles, that propels them. And then, of course, they have stinging tentacles in these parts of their body here. So these are in the group Cnidaria. They're one type of jelly. And then we have another type of jelly. These are in the group Ctenophora. And these move in a very different way. They don't pulse their whole body. Instead, they have, we call them comb jellies, because they have these lines here that kind of look like combs, and they pulse these. They have little paddles. See these little things right here? These are paddles, and they will pulse those. And the rhythm in which they pulse those will propel them. So, and they will then catch phytoplankton. So here's one of them moving. I wanted to talk about another type of zooplankton, just because I think they're really, really amazing. And they speak to the diversity of zooplankton that we see out there. So these are sea butterflies, and these are actually a type of mollusk. So they are related to snails.
For these beautiful little sea butterflies.
If we take them all away, we really don't know what the effects might be, but they may be quite dire for the things that.
So that really speaks to the diversity of zooplankton that we have out there in the neritic zone. One of the things to keep in mind about the neritic zone is it's one of the parts of the ocean that sees a lot of change over the course of the year. Because it's shallow, because it's close to land, we see seasonal change. And changes in the water conditions tend to cause change in the type of species that are found in the phytoplankton. So we see, if we look at this graph here, on the y-axis we have relative numbers, and then on the x-axis we have the months of the year. And each one of these spikes shows a different species of phytoplankton that is basically blooming at a different time. So we can see this progression through the year. We start with one species, and then another species takes over, and then another, and another, and another. Another thing about phytoplankton is that they tend to be found in patches. They're not uniformly distributed. This is really important because zooplankton and animals above them need to have high enough concentrations of them that they can support their biomass. If they were just spread out evenly, it would be hard to get enough food. It would sort of be like having your dinner spread all over a neighborhood. You'd have to walk from one place to another place to another place, and you'd use so much energy to get that dinner that you wouldn't get enough energy from it. Okay, so these tend to be found in patches, and here is a patch. You can see this phytoplankton patch here, where it's in lighter in color. We also can see this is what an area would look like without a patch, and this is what it would look like with a patch. So we can often see these from space. This is the ocean off of South America, and we can see that these phytoplankton, are occurring in these big patches. So what What causes these patches? One of the really important thing that causes these patches um, is the condition of waters around them and the density of water. So we've talked a lot about the idea that we have different densities of water in the ocean, and that can be because of temperature or it can be because of salinity. And quite often what we find is that we have different types of water that are meeting one another, and when those types of water meet one another, that's a classic place to find patches of water. So this is a diagram of the Mediterranean Sea and the water coming out of the Mediterranean Sea. We've talked about the fact that water in the Mediterranean Sea is very, very dense. It's actually super salty, and it's warm but salty, but it's so salty that it sinks even though it's warm. And so it burps out these belches of dense water. And so this dense water here will sink below the water that the other water, and that forces deeper water up. When that deeper water is forced up, well, this deeper water has nutrients in it, and when you force these nutrients up near the surface, you end up having nutrients plus sunlight. So you end up with plankton that grow along this front. So these are called oceanic fronts. When you have changes in temperature or density, they're very, very distinct. And one of those places we see this is in the Mediterranean. Another place that we tend to see it that's close to home is in the Gulf Stream. So we've talked extensively about the Gulf Stream. The Gulf Stream is a warm current and it is moving up into cold water. So we have what's called the Gulf Stream front. We've also talked about these rings, these warm core rings that spin in one direction and cold core rings that spin in the other direction. We tend to see fronts along this boundary between the Gulf Stream and these colder waters of the Mid-Atlantic and New England. So in this diagram, in this satellite image, red means you have a lot of phytoplankton, and green and yellow mean you have some, and then blue means you don't have any. So this is the Gulf Stream right along here, and you can see that below it you don't have, you have very, very low phytoplankton, and then above it you have a very distinct line where phytoplankton are being are being concentrated. You have a patch of phytoplankton there. When you tend to have things like this, it supports a food chain right along these fronts. So where you tend to have these fronts with phytoplankton, you have a lot of zooplankton, and then you have a lot of fish out there as well. So one thing to keep in mind is that we don't have organisms just evenly spread across neritic zones. Instead, we find them patchily distributed, especially in places where we have these oceanic fronts or other conditions that would cause high productivity. A great example of that is right along here. Notice how high the productivity is here? That's because we have so much influence from the land. You have nutrients running off the land. It's very, very shallow here. The perfect place for high productivity. Now, in the neritic zone, we have above our zooplankton, we have our fish and other things like it, like squid or whales, right? So we have our active swimmers. That's what we're going to talk about right now. We're going to talk about nekton, the active swimmer. So let's just turn this on while I'm talking about this. And this is a school of fish, all right? So you can see, you'll be able to see them moving. So schools of fish are very, very common, especially for what we call bait fish. And those would be fish that are preyed on by other fish or by whales or things like that. It's thought that that fish school for a few reasons. The really big reason that we think that they school is to avoid predators. So if you're one big school of fish, it can be very, very hard for a predator to pick out a single fish to eat. Or it's very, very hard for them to tell that you're fish. They might say that's just a big, I don't know, a big whale or something like that, right? So it's a great way to avoid predators. We also know that fish forage better when they're in a school. We don't necessarily know why, but we do know that this is the case, so it's better foraging. It's also easier to swim. So if you're a fish and you're swimming right behind another fish, it's sort of like drafting, right? If you've you ever seen bicyclists in the Tour de France, they'll draft off of one another. So they'll let the first bicyclist break the air, and then they'll get into the draft of that bicyclist, and they don't have to fight their way through the air, right? So we know it's easier for them to swim. We also know that it's easier for them to find a mate. If you hang out with organisms that are the same as you all the time, well, then it's easy to find a mate. You don't have to go and look. One of the interesting questions about schools of fish is, how do they do it? How do they stay in such tight formation? And we know that they use a few different cues. Fish are able to actually feel vibrations in the water from other fish. So that's one way that they could do it. But we actually know that vision is probably the most important part of maintaining distance in a school, because schooling fish all tend to have their eyes on the side of their heads, indicating that they're looking sideways at other fish. Young fish in species that tend to school tend to practice schooling, like they'll get into a small school with just a small number of fish, and then as they get older, those schools will get bigger and bigger. So we think they actually practice this, so when they're young. Now, although you can avoid some predation in a school, you can't avoid all of it. I'm going to talk about 3 exceptions to this, because I think these are really interesting behaviors. And the first one I'm going to talk about is how dolphins, these are actually found only in a few places in the world do we see this behavior. It's using a mud net to catch schools of fish, all right? We do see it in the Gulf of Mexico, so we see it very, very close to us, but it's only found literally in 2 or 3 places in the world. And it tends to be in shallow areas where you have a really, really soft bottom. You can see all this mud being kicked up here, right? So the first thing to know about dolphins is that they are whales. So we have 2 different types of whales. We have the toothed whales, these are the odontocete, right? Odont means teeth. So dolphins are part of this, sperm whales are, killer whales are. And then we have the baleen whales, mysticetes. Mysta means mustache, right? They've got that baleen, looks like a mustache. So dolphins are a type of whale. And in this behavior, we have a driver dolphin. Now, interestingly, the driver dolphin tends to be the same dolphin over and over and over. And there's a lot of interesting questions about, why would this guy help all these other dolphins? Because they're not always related to him. So it's an interesting question to know, like, why is this guy helping these guys? He should only be really worried about himself or close associates, like a brother or a sister, or his offspring or her offspring. So this driver dolphin will basically herd a school of fish into a small ball. And in this video, we're going to see this dolphin is using this ring of mud to drive them into a small ball. And they kind of freak out. So these guys freak out and they'll jump up into the air. And then all these dolphins will grab them out of the air, literally grab them out of the air. So let's take a look at this video to see mud plume feeding.
These dolphins have worked out that fish out of water are much easier to catch.
So this is our group of dolphins, and the driver dolphin is about to start driving fish into a small ball. So you see how he's using his tail to kick up mud?
By beating her tail down hard, this bottlenose dolphin stirs up the seabed.
There's a school of fish in the middle of this circle.
And by swimming in a circle,
and you can actually see
she
he's
creates a
looking
ring
at those fish.
of mushrooming mud around the shoal of fish.
Also using echolocation to
the
know
fishing
where he's
net,
going.
made of mud.
Right. So now these dolphins are all going to come over to the net.
As the net pulls tighter and
watch
tighter,
this.
the fish
Watch
are
the
trapped.
fish here freaking out.
Till there's only one way out.
See all that activity? That's them grabbing
Straight
fish. Oh,
into the
yep, we got one.
mouths of the waiting dolphins.
So that's a pretty cool behavior that allows dolphins to overcome the difficulty of hunting fish that school as a group. let's take a look at another behavior that's actually very, very similar. So these are humpback whales. Humpback whales also will catch schools of fish, and they will use a similar method. Rather than stirring up mud in a circle, they will blow bubbles, and then we'll use what's called bubble nets. So these guys here, some good footage of bubble nets. You'll notice they're surfacing right in the middle of that. So they go down deep. They blow bubbles in a circle, and that makes sort of a wall or a net that the fish can't get out of. And then they will surface under that, and they will, you can see some of these guys have their bellies distended, so they've just taken great big gulps of yeah, full belly, great big gulps of water, and he's lifting out fish from that. So let's take a look at this footage is actually really nice because you can see here that he's got it. There we go. So he's got a really nice bubble net going on here that he has blown, and then he's actually, when he comes up, he's using his flipper, these great big flippers, to also corral fish so he can get a great big gulp of them. Now watch, here he comes in and he's using his flipper. And you can actually see his mouth open. See this mouth open right there? So he's driving that school of fish into his mouth so he can get a great big gulp of food. All right, our last bit of footage here of animals that are feeding on a school of fish is actually what we call bait ball feeding. And this is just really incredible footage where you have a school of fish that are desperately trying to escape being fed. And the ball of fish, the bait ball, the school gets smaller and smaller and smaller. And all sorts of things are feeding on these sardines. So these are little tiny schooling fish, and there's seabirds, there's sea lions, there's sharks, there's dolphins, and then there's this whale too. So let's take a look at this.
Copper sharks. They've scented blood in the water. Surprisingly, perhaps, the predators never attack one another. They work together to corral the ball of fish, taking turns to grab a mouthful. Common dolphins. As the shoal gets ever smaller, each sardine scrambles desperately to hide in the middle. But now there's no escape. A brooder's whale finishes off the feast. Tons of sardines devoured in less than an hour.
Okay, so that's a rather dramatic bit of footage there of an entire school of fish being fed on and being eaten. So schooling can be really helpful in avoiding predation, but it also can, if you are a predator and you know how to take advantage of schools of fish, it can leave you vulnerable as well. Now let's talk about the bottom of the neritic area, and this is what we call the sublittoral zone. So the neritic zone basically goes from shore out until you get to the continental slope. And we've been talking about sort of the nekton of that, which is the free swimming things, but let's talk about the bottom, all right? What we tend to see, and we've talked about this when we were talking about ocean sediments, we see a difference in the type of sediment depending on how far away you are from shore. So close to shore, you have a lot of influence from the water, from the turbulence and currents and tides, and then far from shore, you have less influence. So you have different amounts of energy that are impacting the bottom. Here, close to shore, you have high energy, and far from shore, you have low energy. And we have big things, only big things will settle in high energy. In high energy waters, mud will stay suspended, but big things like coral or like gravel or larger sand will sink, right? And then out here, this is where we end up with having just the mud settling. So you tend to see differences in ocean sediments. And because of that, we tend to see differences in the types of things that will live there. Close to shore, we tend to see a lot of filter feeders, okay? And let's look at this here. Close to shore, we tend to see a lot of filter feeders, but then we see less of them as we move offshore. And then offshore, we see a lot of deposit feeders, but we see less of them as we get close to shore. Now, filter feeders will actually grab particles out of the water. We've talked a little bit about filter feeders in the past, like barnacles or mussels or sponges, right? So they will grab things right out of the water, and deposit feeders will grab things off of the bottom, all right? So why do we see this difference in the type of things that live in gravel versus in mud? Well, first of all, when you live close to shore, you have very strong currents. And that can be great if you're a filter feeder because it means that things don't settle out of the water. So the plankton that you want to eat stays suspended, right? So there's a lot of things to eat there in the water column, right? Contrast this to out here, there's weak currents, and so we see things settle to the bottom. So plankton will settle, detritus will settle. So if you were trying to filter feed out here, there wouldn't be anything to filter out of the water. But if you're just eating stuff off the bottom, well, you're in luck because a lot of things settle. Also, if you live close to shore, you can't accidentally eat the sediment because it settles so fast. So you can't suck sand in or anything like that, right? But if you were to live out here, you could accidentally suck in mud, all right? So you would actually clog up the apparatus that you use to feed. So that's another reason that we tend to see this difference here, all right? So we tend to see differences in assemblages of types of things in the bottom. Let's just take a look at the difference between a filter feeder and a deposit feeder. We've seen some filter feeders in the past, but let's take a look. This is a sponge that is filter feeding. I think it's really nice footage here. This is a diver who's putting that floor.
How the water is moving by watching what the dye does. Within only seconds, the dye is pumped through the sponges along with the water. As you can see, a sponge is a pretty good water pump and also a good strainer. Any plankton that goes in with the water won't come back out through the osculum.
Okay, so that's that guy who is filter feeding. Now, this is a deposit feeder. This is a sea cucumber, and this is footage that I actually took. So this is his mouth here, all right? And then his mouth is surrounded by all of these tentacles. These tentacles have like a sticky mucus on them, and you can see that they get really, really fine at the ends, right? And he'll put these out whenever he thinks there's food, right? He can actually pull them all in if he wants to. He'll put them out. They're sticky. Things will fall down onto them, or he'll put them down on the bottom and he'll pick things up with those. And then he actually will take one of those tentacles at a time, put it into his mouth, and clean it off. It almost looks like he's licking his fingers. Like if you ever had something really delicious, like barbecue or something like that, it looks like he's licking his fingers. So let's take a look at this guy. You see he's licking one of his tentacles there, and the other ones are out deposit feeding. And here comes, one is coming out and another one is going in to be cleaned and have all the food eaten off of it. And then as that one comes out, another one goes in. And he'll just do this for hour upon hour upon hour. All right. Let's move from the continental shelves to the offshore realm, okay? Let's move away from shore. As we move further away from shore, we have differences in the importance of different types of phytoplankton. So here we have the number of cells that you find in 50 milliliters of water on average. And here we have distance from shore, starting from the coast and going towards the open ocean. Close to shore, diatoms are very, very important. Around the continental shelf, dinoflagellates are becoming important, and coccolithophores are becoming important. Then as you get out into the open ocean, you can see that the importance of these three different groups are pretty equal. Diatoms are important, dinoflagellates are important, and coccolithophores are important. I can tell they're equal because each one of these lines here is about the same length, okay? So let me just remind you what coccolithophores are. Here's an individual coccolithophore. This is a type of algae that is surrounded by calcium carbonate plates, all right? So it makes a shell for itself. And these are microscopic, they're very, very small. And these shells are white. Interestingly, when you have a lot of coccolithophores, when you have a bloom of these, they actually change the color of the water. And so here's a bloom of coccolithophores. This is close to shore, so we are going to talk about offshore, but I could find this picture close to shore. This is in Alaska, and Alaskan waters do not look this bright turquoise usually. They look more blue or dark green, and they look like this because this white shell of millions upon millions of coccolithophores is reflecting sunlight here. We can actually even see this from space. So this is also in Alaska. This is in the Bering Sea. And this is a bloom of coccolithophores. You can see this bloom right here. And you can see that it has caused the water to look this sort of light green or turquoise green. And that happens when we have a lot of coccolithophores. Now, in the offshore realm, we also have zooplankton. We tend to not have the same type of zooplankton that we have on the continental shelf. One of the really important types of zooplankton that we see out in the offshore realm are something called krill. And this is a krill, an individual krill. They kind of look like shrimp, right? They're closely related to shrimp. They're arthropods. And one of the interesting things about krill, another word for these are euphausids, is that they tend to occur in these bands where you have a lot of influence of latitude. So we have one type of krill here along the equator, and then as you move away from the equator, we have different species that come into importance. These are sort of the basis of the food chain out there. Let's move up the food chain and start to talk about some of the fish that we see in the offshore realm. So, interesting things to know about the habitat out there is that the habitat is featureless. It's not like a coral reef where you have, nooks and crannies and cliffs and all sorts of different little niches for organisms to live in. It's featureless, right? It's all the same. There's very low habitat diversity, that means. And where we have very low habitat diversity, we typically have very low species diversity. This is one of the patterns that we see in nature, all right? And this is true in the oceans. So only 2% of the fish species is found in the epipelagic habitat. And that doesn't mean biomass, that means the number of species, all right? Even though the open ocean takes up most of the world is open ocean, Less than 2% of fish species are found there. So that suggests there's just very, very low species diversity. The open oceans also tend to be nutrient poor because most nutrients come from either land or places where there is upwelling because we have land. And so we don't have a lot of nutrients in the open ocean. And that means we typically have low productivity as well. So we don't have these gigantic food chains with gigantic schools of fish. Those tend to be found closer to shore. So these are some of the characteristics of the epipelagic habitat. Now let's take a look at some of the fish that are found in the offshore realm. So this is a bluefin tuna. This is a mackerel, and mackerel, actually, these guys love to eat mackerel. This is a swordfish here. Actually, swordfish love to eat them too. These are relatively small, and this is larger, and then this is huge. This is like 1,000 pounds. Actually, these can be huge too. So one thing you'll notice about them is that they have very similar body form, right? So they have a fusiform body. That means they're torpedo shaped. They are streamlined, right? They don't have. Compare this to like our friend the lionfish, who have a lot of things sticking up off of them. They don't have any excess fins or anything like that. All right. They also tend to have high, narrow tails. See how they all have the same type of tail here? They have this thin tail that is split. These are really efficient for swimming, and they tend to swim. All the fish in the open ocean tend to swim by moving their tail back and forth. All right. This makes all of these fish really efficient swimmers. They're really, really fast. They're good at swimming. And that's important. So if you live in an environment that's featureless and you're this guy and a lot of things want to eat you, right? You don't have any place to hide. You can't hide in a little nook and cranny of a coral reef or anything like that. So your best strategy for avoiding predation, if you're this guy, if there's no place to hide, is to be able to move really, really fast. So these guys need to swim fast to avoid being eaten. Of course, these guys need to move fast, and these guys need to move fast so they can catch this guy, right? So all of these fish tend to swim very, very efficiently and very, very fast. They also move long distances. They cover huge, huge distances in the oceans, and that means they need to be efficient, all right? So that's another reason that they need to be good swimmers. Another characteristic that you will notice about especially this guy and this guy, one of the typical things that happens in epipelagic fish is that they tend to be counter-shaded. And we actually see it in other species as well. Killer whales are counter-shaded. Penguins are counter-shaded. And that basically means that you're dark on the top and light on the bottom. So if you can see, this guy's dark on the top, light on the bottom. Same thing for this guy, dark on the top, light on the bottom. And what we think that's for is to avoid detection by either predators, if something is going to eat you, or your prey. So imagine that you are this bluefin tuna, and the ocean is the surface of the ocean is way up here, and your prey is here. When your prey looks down at you, well, you're dark, so you are blending in with the dark bottom. Now imagine that your prey is down here, and your prey is looking up. It's seeing your light belly against the light above you. This is what we think counter shading does to help organisms. So that's a typical thing that we see in open ocean swimmers. I talked a little bit about the fact that these are very efficient swimmers, and let's just give you a couple of examples. So this is a tuna that was tagged, and over 600 days he crossed the Pacific. He didn't just cross it, but he did a bunch of maneuvers in here, probably taking advantage of prey in here, right? So over 600 days, which is about a year and a half, a little bit more than a year and a half, this tuna traveled almost 25,000 miles. And then here's another example. So this is from the O Search group, and these are two white sharks that have been tagged, and you can see that they are moving huge distances, all right? And they're moving huge distances looking for food, probably following food, finding patches of food. So these guys tend to travel long distances across the oceans. Now, interestingly, one of the things that fish like to do out in the open ocean is they like to aggregate around floating objects. So this is a log that's just floating out in the middle of the ocean, and you can see the huge number of fish that are near it. If you moved a mile away from this, you would find no fish. They tend to like to hang out near these floating objects, and we don't know why. If you are a fisherman who's trying to catch some of these fish, one of the things that they used to do is they would throw logs in the water and they would set nets around them because so many fish would gather there. Now they don't use logs, these are called fish aggregation devices, and these are there's a lot of controversy over these because not only do you tend to get fish, but you often get things like dolphins, or you tend to get things like turtles who are aggregating here as well. And those animals get killed when fishing is occurring. Okay, folks, we're going to stop there for now. This seems like a good stopping point. So as usual, stay safe, stay healthy, and I will talk to you soon. Take care.